Hey guys, what's going on? So today we're going to be talking about topology within the context of Chern Simons series, what we're aiming towards. But I just want to kind of go over topology in a broad sense. I'm going to try to get at this topic of topology from also a sort of different angle. And because I think topology is somewhat of an abstract, obscure thing that is often not really picked up very easily. And so I'm going to try my best to use fish as an analogy to understand topology. And so with that being said, let's go ahead and get started. Make sure to hit that like and subscribe button. Make sure to become a member on my Patreon page or YouTube, or become a member on YouTube here, and you can get exclusive content. All right. So, what is topology? So this is going to be there's going to be some math involved here, but there's also going to be just a lot of words involved also that I want to get across to you guys. So I'll be reading some of this and I'll explaining some mathematics. So what is topology? Well, in Greek, the prefix topos means shape, and thus topology is the study of shapes. So, and most people are often told that topology studies the number of holes in something, or how coffee cups are the same as donuts. Well, this doesn't really get us anywhere. Okay, to me, whenever I go onto YouTube or read something about topology, I'm always presented with the coffee cups and donuts thing, and for the longest time I felt like this wasn't going anywhere. It wasn't getting anywhere fruitful for me. So I kept on trying to push through this, and this is what I'm going to present to you, how I see topology, and I think it'll be a lot easier and a lot more fruitful. So let's continue. So in order to get beyond these playful images into real-world applicable situations, we need to understand that the core of topology, we need to be able to, at the core of topology, we need to be able to abstract our thinking from coffee cups to vector spaces. And the most common vector space that we know of is Rn. That's the real numbers, and it's 1, 2, 3, 4, 5 dimensional, right? So Rn again being, let me just decrease the thickness of my pen. Rn being your typical Cartesian coordinate system, right? You have x, y. This is R2, right? So R3 is going to look like x, y, and z. Realize I say Z sometimes. I'm not British. For some reason, I just say that. Okay, anyways. This vector space is a vector space that we all know and love. We're most familiar with this type of vector space, and it's very useful. It's a very useful thing for us. However, the laws of physics should not be violated if we choose a different one, or if we choose a different vector space to describe some system. And that's the first thing that we sort of have to understand, I think, is that no matter what system you use, it could be Rn, it could be S2, it could be any system or any coordinate system, the physics doesn't change. That we need to ingrain that into our heads, I think, because the relationship between different coordinate systems is actually going to give us interesting physics, okay? So in other words, we should be able to bend and warp and manipulate Rn in any way we want and expect the same physical description of reality. We could, for example, describe reality using a sphere. This is often done using a stereographic mapping. In this mapping, every point is mapped onto the surface of a sphere in some particular way. And so with stereographic mapping, you take the pole of the sphere and you draw a straight line from the pole passing through some point on the surface of the sphere, and the line between those 2 points is what gives you a point in Rn, right? So the plane here, this is this is R2 actually, right? So this is going to be R2, right? Because R2, right? Because we have x and y. And then our sphere is S2. Okay. Depends on if the sphere is hollow or not, but we'll just call that S2 for right now. Okay, so we can regard all of the points in the 2D plane to be members of a phase space or a complex space that describes perhaps some quantum state, right? So it could be phase space, it could be quantum mechanics, but if we're doing this, we have to make sure that physics is not violated when we do this kind of thing. But again, these are just spaces. We can use these spaces to describe any sort of physical system. The mapping should preserve the physics of the system. If during the mapping process there are no breaks or tears in the 2D plane, then we can regard the 2D plane as topologically similar to the sphere. So let's consider how we can think of vector spaces in some more complex shapes. Okay, so here we have a table. This table shows us we have a sphere. Let's get rid of that. Or not a sphere. We have a rectangle. Suppose we identified this side with this side, and they're oriented in the same direction. Okay, and when we identify A with A, or this side with this side, we call this side A. This is also A. So that means we can take these two sides and sort of wrap them around and glue the edges. And when we glue the edges, we get something that looks like a cylinder, right? So that's our shape, is our cylinder. And then we'll get into this column later. Let's just finish the shapes here. So in this case, the boundary conditions are different, right? We're identifying A here with A, but on this side, it's alternating, okay? So they're again, this can be thought of as alternating boundary conditions. And so when we do that, you take the strip, you flip it, and then you glue, you get a Mobius strip. Now, if you don't know what a Mobius strip is, it's a one-sided shape, essentially, okay? There's a lot of interesting things that we can talk about when it comes to Mobius strips, but we're not going to do that right now. We're going through this table just to really understand how boundary conditions play a role in topology. Okay, so let's take the torus now. The torus is really just a cylinder, right? So we identify A with A, but then we wrap B with B to each other. We glue those ends together, and what you get is a torus, right? So this is what a torus looks like. And again, we have repeating boundary conditions, right? Because they're oriented in the same direction. Okay, now the Klein bottle. The Klein bottle is weird. So we have A and A. So we wrap those two across each other. This is sort of hard to visualize. But then B and B here, those two are alternating. So we have alternating boundary conditions in one dimension, but non-alternating in another dimension. And what you end up getting is the Klein bottle, right? This is hard to visualize. Going from this to this is hard to visualize, but this is what you get. Okay, so we've identified these now with what type of boundary conditions we're looking at. So if we have something in a physical system, for example, and in physics, in the real world, if you have something that's, say, oscillating, you have alternating boundary conditions, then you could use, say, a Mobius strip or maybe a Klein bottle to model your system. If you have repeating boundary conditions like a sine curve or something that's just repeating, then you can use perhaps a cylinder or a torus or a sphere. Maybe a sphere is you could use any one of these to model something that has repeating boundary conditions to it. All right. We can see that topology really begins to become useful when we consider boundary conditions and the notion of what a boundary condition is for some sort of system. If electron states rotate between spin up and spin down, for example, we can think about describing this situation with using a Mobius strip, which is sort of what I talked about a few seconds ago, right? Because you have, if you consider a Mobius strip, you have spin up, and then as you travel around the Mobius strip, this arrow that's always orthogonal to the surface eventually comes and it's facing in the opposite direction. You do it again and it's going to face up in the opposite direction again. So that is an example of something that has alternating boundary conditions. For a torus, we might consider a system in which initial conditions are identical to or to the final ones in any direction, right? So the torus, there's no flipping in these green arrows around this edge, and there's no flipping in the red arrows either, right? So U1 Chern Simons theory, because we want to talk about Chern Simons theory here, can be described using a two torus. So the torus with two holes. Although this might be somewhat difficult to understand because we haven't covered this yet. A very simple way to view this, though, to view this system in which its x and y coordinates are periodic, you can have you can have two-dimensional waves that might have this property. So what about a system with x, y, and z coordinates that are perhaps periodic? Well, this becomes difficult to visualize, but for a multi-particle system, we can visualize it perhaps in this way, right? So you have these pentagons, right? So we're doing something like this, but we need these pentagons because we're going to glue some things together, right? So particle 1 could have alternating boundary conditions, right? Particle 2 could have some alternating boundary conditions. So this shape plus this shape is actually going to give you the two torus, where the glue point is right here, right? And we do the same thing for it looks like I'm doing different colors, right? So this side and this side, and then this side and this side. So that's going to be this guy right there. For a system of x, y, and z coordinates, well, this becomes a little bit tricky, right? Because we had here we have alternating boundary conditions for x in the x direction and in the y direction. If you add a z direction, well, then you have to add another. You essentially have to have a three-dimensional shape, and then when you do this and you start adding them together like this, the topology becomes really weird. So what we need to do is formulate something like an algebraic topology, or form some sort of algebra that's going to give us algebraic topology, which is where eventually we're aiming towards. We want to be able to add and subtract spaces to each other so that we can be able to understand systems by these topological spaces. Okay. All right. Let's talk about fish now. But before we talk about fish, what does it mean? What do the topological holes really represent? Because when we're looking at these toruses, well, we could say, well, it's all fine and good. We can add and subtract these shapes, and we can get these interesting topological shapes, these 2 toruses, 3 toruses, and 4 toruses, and 5 toruses, and so on. They have these holes in them. Then you could ask the question, what the heck do these holes correspond to in the physical world? It took me a while to sort of have this click, but I found a paper. There's a beautiful quote from a paper called Topological Defects in Biological Matter. I'm going to butcher the names of these people, but it's Alexandra Ardaseva and Amin Dust. I'm not going to even. I don't even know how to pronounce that. If you guys know what language that is or what ethnicity that comes from, then let me know in the chat below. But here's a quote: "Nature relies on the subtle balance between order and disorder. In condensed matter systems and in high-energy physics, the breakdown of order can lead to the formation of topological defects, singular regions where the order parameter collapses. Because of their topological nature, these defects are protected against structural deformations, and their removal requires energy. No smooth rearrangement of the order parameter can eliminate the topological defects. Again, if you can hear my dog, I'm sorry about the dog. He barks way too much. But this was a very interesting quote, and I thought it takes energy to tear something, right? So because when you're talking about like donuts and coffee cups, oftentimes what's put into the milieu of that language is if you tear it, then all of a sudden this isn't a topologically invariant thing that you're dealing with. So it takes energy to tear something, right? And these holes, therefore, can be thought of as these things called topological defects. These are singular regions where the order parameter collapses, right? In terms of this quote here, to me, this means there's no smooth rearrangement of this parameter that can eliminate that defect. So you could sort of think of, if you're say maybe thinking of some semiconductor, a topological defect in this semiconductor could be something like some particle that shouldn't be there, right? So you could have what's the word I'm looking for? Inhomogeneous. So something that's adding inhomogeneity to the surface that could be regarded as some topological defect. So thinking of these topological holes as defects in the context of physics, I think, does a really good job at illustrating their physical interpretation. The boundary conditions place restrictions on the number of states that can be accessed by any system, which introduces these holes or these defects. And so one can regard these topological holes or defects as stable configurations of matter that are only broken at very high levels of energy. So this would correspond to the ripping or tearing of the transformation that fundamentally changes these shapes. Okay. Let's try to illustrate the importance of topological defects using fish. Now, I love fishing, so this example, when I found it, sort of really hit home with me. It gave me an aha moment. So let's go through this. The thing that we want to remember throughout this analogy is the notion of continuity and orientation. Suppose we have a live well box of fish. Now, if you don't know what a live well is, it's just something that you put fish in to keep them alive while you're motoring around in your boat. These fish can be oriented in any way, but let's suppose that we are just interested in the fish along the boundary of the box. Okay? So they could look like this. They're all swimming in one direction. Schools of fish tend to do this. Okay, so we can now ask the question, what are all the possible ways, again, my apologies for the dog, what are all the possible ways that the rest of the fish inside the box, or the interior of the volume, can be oriented? We need to assume, however, that the fish adjacent to each other only differ in their orientation in a continuous way. And what do I mean by this? I mean, take these fish, all right, and you have, you're nudging every fish adjacent to another fish is just nudged in a particular direction. So you look at this example, and you nudge this guy is just a little bit this way a little bit, and he looks like this. You nudge this guy a little bit more, it looks like this. So all these are just little nudges of fish, and any direction you go, you have these just slight nudges of the fish. Okay. You don't have a quick flip, a 180 flip in the orientation of the fish anywhere, okay? However, you do right here, because here, these two fish, if you were to think of them as adjacent, right, so fish 1 and fish 2 here, if you were to think of those two guys as adjacent, well, this is a 180 flip. Same thing with this guy here, 3 and 4. Those are 180 flips in the fish also. So here's a point. This is our topological defect. In this case, there are no dramatic jumps between any adjacent fish, but except in the center here. In this case here, however, there are dramatic jumps between any adjacent fish, and so we're not going to allow for this situation to happen. What we want to allow for is continuity. Now, if you assume continuity, we'll So continuity really places a big restriction in terms of mathematics, right? But what this means is that you're going to have one hole here. You've minimized the number of holes, okay? All right, let's continue. So we can see that in the left panel, right, so this panel here, a fish at the center would not know which way to look, right? You can't put a fish here. You can't put a fish right here and expect complete continuity, right? Because if he's looking in this direction, right, if he's looking in this direction, well, that means this fish and this fish are going to be 180 flips from one another. If he's looking in this direction, well, that means this fish and this fish 180 flips from one another, right? So the idea here is that, again, we need continuity, but that one particular fish at the center doesn't know which way to look, and so this is what you would call a topological defect. And if we allow for this continuity of orientations, then we'll get a topological defect. The orientation of these fish can be placed on a complex plane also. We can illustrate this mathematically. So if a fish is pointing in this direction, as opposed to a fish pointing in this direction, well, this is just a circle on, say, C2, or just the complex plane, right? Not C2, it's C, complex plane, and if the orientation is modeled in the complex plane, we can say, well, the orientation then is given by x plus iy, or e to the I phi x, right? Each fish has its own orientation, so we can integrate over all of the orientations along the surface, and when we do that, we get, what we ultimately get is going to be the circumference, right? So as we integrate over the surface of this live well box, f of x winds around the entire unit circle. And so if f of x is continuous, then all of the solutions, that should be all of the solutions of f of x is an integer of z. And so integrating all these fish, all these fish is going to be just related to the circumference of our pond or of our live well box. And this is z, where z again is that's just an integer. So it's an integer number of the circumference. So we've effectively seen an example of topology now turning geometry into counting. We can now reintroduce differential forms, and when we do that, we have an orientation. Differential forms, again, give us, they have an orientation to them, and this gives us and this is given to us by the sign of the differential form. If you recall the definition of a form, it looks like this, right, where this this notation, this wedge notation, infers this. It's the difference between two tensor products. And so if a wedge product between any two vectors is negative, then this means that we'll have a negative area, which we'll call an oriented area. And so another way of thinking about this is that if you have vector u and v and you take the wedge product between them, well, that's an area. An area can be oriented in this direction or in this direction. And the sign of this guy is what's going to give us, the sign of this guy is what's going to give us that orientation. All right? And so we can see now that one fish represents a wedge product because they have orientation. Imagine now gluing two ponds together. We can see that the surface, at the interface of the two ponds, or the two little boxes, I keep on interchanging ponds and boxes. Just think of them as two live well boxes, okay? We can see that at the interface, the fish are oriented in opposite directions, and so their values will cancel out, right? Because we have arrows. So suppose these guys are pointing in this direction, these guys will have orientation pointing in the opposite direction. And so this is going to result in us being able to effectively ignore the fish at the interface. when integrating over a boundary. Okay? So we ignored the oppositely oriented fish at the center, and we could see that integrating will give the circumference of the live well box, and that'll give us the circumference again. The circumference is therefore related to the number of topological defects. This is an important point. This means that the differential forms are a way of converting circumference or surface area to topological defects. Let that sink in for a second. What we're saying is that the holes in, say, a 2 torus, that the number of holes is directly related to the surface area if we use differential forms to integrate over the area. This is actually quite interesting, and this is what's going to lead us into algebraic topology, differential topology, and all this sort of stuff. So lastly, I want to mention the concept of a non-orientable manifold. Most objects encountered in the physical world are orientable, but some objects are not. These objects include Mobius strips, real projective planes, and Klein bottles. And for these objects, you can't really define a consistent orientation of fish on these. So you take an orientation of fish, for example, on the boundary of this thing. Well, at this point here, you have this topological defect. So we run into this defect on the surface itself, which means that the Mobius strip is a non-orientable manifold. All right. So that is an intro to topology, where we use fish. So that was quite fun. I'm a big fisherman myself, and I think coming up with this example was actually quite interesting, and I think it gives us a lot of insight. The next things we're going to do is we're going to dive deep into into 3 concepts. 3 very important concepts. These are going to be the 3 invariant topological invariants. 3 topological invariants. 3 topological invariants. 1. If you're not, you might know where I'm getting with this, but 1 is homotopy. That's going to have to do with the connectedness. 2 and 3, homology and cohomology. Once we talk about these guys, then this is going to be the green light into talking about Chern Simons theory and go deep into Chern Simons theory. Because again, Chern Simons theory is essentially is by nature a topological theory. But so if it's a by nature topological theory, we need to know these invariants. These are topological invariants that are going to be very interesting to us. And so with that being said, I hope you hit that like and subscribe button. Hit the like and subscribe button if you want to. Also become a Patreon member. That helps in creating more content. That also helps in making this channel even bigger. You can become a member here on YouTube as well. And so with that being said, I'll see you guys in the next one.